Right, 17.
Hi, Dr. Chen.
Is it possible to send a invitation, like a calendar, something, I can save the calendar. So every time I access, I need to looking for your email.
Okay, yes, I will.
I can give the email, I couldn't save in the calendar. I'm not able to save the file in my calendar. So if you can send a file invitation, like something like you can, like a lot other people invitation to me, they can direct save it into the calendar.
Okay,
Right.
okay, yeah.
Way one thing is you don't need to create it like a like a Google photo for me. I just told them, okay.
Oh, okay. I thought maybe it's more easier.
I try to push them send me the file as soon as possible.
Oh, okay.
Sometimes you know sometimes because they promise me they send everything to me by Friday.
Uh-huh.
But but hopefully, D-man can working hard, because I already finished the proposal, but however, their part I did not finish yet.
Okay.
For them, the 15 page, I writing most the 13 page. If they
Mm-hmm.
can send to me, I can add in after this. I also do some other editing. Today I get the budget down. Okay.
Okay. I see.
Good. Okay. Sorry. So
Um,
many people is online. Good.
so currently three. Hi everyone. Uh, Glad to see you here in our MAR 512 class. I see you are all from Professor Wu's club lab, right?
Yes, right.
Yeah.
Oh, that's cool. So earlier today, I also received email from Yunji. So she told me that she will not be here, right?
Yes, right.
Okay, okay. So I assume maybe today, so far we only three students will join this discussion, Dr.
Mhm.
Chen. Yeah. So how about we start with the introduction? Uh, So maybe I will go first. So hi everyone, I am Cici Li from University of Massachusetts, Dartmouth. I work in Dr. Changsheng Chen's lab as a associate research professor. And thank you so much for joining this discussion. And Dr. Chen, your turn.
Yeah. And Changsen Chen was the professor, was in SMS, UMSD. So, I probably you know me, right? I'm not sure I meet all of you. So I come here, for if you have any question for FVCOM for the class you take. So we happy to address the question. Professor Lee and I can address both your question. Both we can address your question. Okay, good.
Okay, so Ming Wu Park.
Oh,
Um,
yes.
could you please introduce yourself?
Uh, okay. Oh, Glad to meet you. My name is Minu Park, and my
Mhm.
my research area is the sea cold yellow spot cold water. And uh thank you.
Mhm. No
Okay.
problem. Okay. You just try to, I told you, Kim, when last year, so you had a couple Korea students take the course. At the beginning, they couldn't speak, English, well. However, after one semester, they can, after they try, they can do pretty good job. Okay. I had a student, come from your lab, called King Wang, right? King Wang. So now he can speak English very good. Okay. He can ask a question, he can take the class and no any problem. Okay. Okay, good.
Yeah, so next, Jin Yun King. Do I
Okay.
pronounce?
It's nice to meet you, Professor Chen and Dr. Shiri. I'm Junyoung Kim, a master student in Professor Wu's laboratory.
Mm.
And I'm interested in coastal water temperature, and especially I'm trying to study uh, how tidal floods affect nearby water temperature. Yeah, yeah. Thank you.
Thank you. Okay, so Yong So Jin. Sorry, I can't hear you.
You just mute. Mute. Oh, yeah.
Okay.
Yes.
Glacium, Professor Chen and Professor Lee. My name is Yoon Song Jung, and my research area is Gyeonggi Bay, and I'm interested in two energy methods. Okay, thank you.
Okay.
Okay. So nice to meet you, everyone. So, you're for this discussion. So since this week, we will hold the discussion like this one every week on Thursday in US zone and on Friday morning in South Korea zone. And during this discussion, you may raise questions about what you have in the last week lecture. So for example, today, if you have any questions about the lecture 1, 2, 3, feel free to ask it to Dr. Chen, and then Dr. Chen and I will answer them. And also, if you have any question about the FVCOM of your own project or of your own case, or if you have any questions about the ocean modeling, and physical oceanography. So you can also ask it here. So one thing I want to mention is that in our online course, we also have a discussion board. So sometimes you may also raise questions there to just set a new question. And when I found the question, I will answer them as soon as possible. In that way, other students can also see the questions and see the answers. So that may also help other students. Okay, so that's all from me. So, Dr. Chen, do you have any other things to mention?
No, I don't have. Just if a student have a question about the lecture you're taking, you can, you can easily, we had a blackboard, right? Remember before if you couldn't speak clear, you can do, you can put question. Remember we had a question board, right? At least, remember we need to go to our, my course site.
Yes, we have the discussion board.
Discussion board. So you can pose a question on the discussion board. I think you can access right now. So we can look at discussion board, see what question you have. Sometimes the student just the beginning, they probably not shy to ask a question, on the screen, but they can typing on, okay, on a question on a, was into the my course, the discussion board. So then we can address the question, just like last before, right? We did a pretty good job of that. Yeah.
Yeah, so I just show how to get access to the discussion
Yeah.
board.
Yeah, I think you can describe how they can post the question in this board, and so they can post the question before they join the discussion, or they can post the question on the discussion. Okay.
Yeah. So So now this is my course page. So first you log in with your UMass account and then select the FVCOM course. Here, these are all the lectures for every week. And at the bottom, there is a tab called the course tools. So please click that. And there is a discussion board. So after we into the discussion board, please click this number. And here we have already create all the tabs for each lecture. So if you have any questions regarding some certain lectures, please feel free to ask them here. So, for example, I have a question about the lecture 1. So just click it. And then here, click the create thread. And then here you can write your subject or title. So after that, just raise your questions here. You may also post some figures or post some web link. And after that, just click the submit. And then you can see here, so that everyone will see your questions. And also, when I found your question, I will answer them as soon as possible. Okay, so I think this is a good way for us to share the questions and solve them. As Dr. Shen mentioned, so it would be great for you to write your questions here as early as possible, because in that way we can solve your questions quickly.
Yeah.
Yeah.
You
So
can write down the question, leave it there. So then, you can write. All right. So you can write and then post the question over there.
yeah. So do you have any questions about the past few weeks, say from lecture 1 to lecture 3? If you have any questions, so you may just ask them here now.
Yeah.
Oh, yeah, okay. Although I think it's not directly related to the lectures, but
Mm.
I have a question.
Okay.
That's okay.
Can I share my screen?
Yes,
Okay,
Definitely.
go
thank you.
ahead.
Okay, thank you.
No, you can ask any question. You can ask a question about class. You also can ask a question about the model.
Okay, thank you. Can you see my screen?
Yeah, I can see that.
Okay.
Yeah.
So I ran a simple idealized test,
Yeah.
and in this idle domain, which looks like tidal flat, I
Mhm.
only applied elevation and
Mhm.
radiation heat as external forces.
Mhm.
Um, oh, I'm sorry. When looking at a vertical
Mhm.
slice, then this thin layer
Mhm.
represent the temperatures of dry nodes. And
Mhm.
I found that the radiation itself doesn't directly change their temperature, but instead, it seems like the temperature changes because of the wet-dry transitions of the node. But I'm not sure about the exact mechanism behind this. And secondly, I'm wondering if these dry node temperatures have any effect on the water temperature at the bottom layer.
Mhm. Okay. So, Dr. Lee, you want to address the question? You want me to address the question?
I think I can address the question 1. So in FVCOM, when we treat the wet-dry point, so actually there is a special lecture in this semester talking about the wet-dry treatment of the method in FVCOM, and also other methods in the other models. But here in FVCOM, when we treat the wet-dry nodes, so no matter this one node is wet or dry, there is always a layer let's say if this point is considered as a dry node, it means that the total water depth is smaller than a certain value. For example, in the name list, you may set it as 5 centimeter. So that means if the water total depth is smaller than 5 centimeter, then it is considered as a dry node. So in that situation, although there are still the water temperature archived in your output NetCDF file, however, it is not actually a true temperature, so you may just ignore it. So for example, here on your figure, I see that you make an animation with the temperature changing over time. But however, when the water surface elevation is down, you still draw the colors on the dry points. So you may need to also read a variable called wet node. So in that way, you can find out which nodes are dry and which nodes are wet. And after that, you may just need to draw the wet nodes.
Okay, thank you.
Now, one thing I can add for this, in the FVCOM designing the wide dry pond, so when the water flooding from the wet to dry, right before the dry, so then the temperature just be adapted from the wet pond to the dry pond. When the water withdraw from the dry to the wet, withdraw, the water out, like down. So then they become the water region become from wet become the dry. Before the dry become the wet. That's why the prediction is conservative because the water was advanced in, right? So then reverse process when the water become from wet become to dry. So after become dry, so the region supposed no temperature, right?
Yeah, right.
However, we cannot do that. If you do the zero temperature, so that region could be the trouble, right? Because next
Yeah.
time you have water flooding in, you get a big grading, right? Because of from zero for something. That's why in the FVCOM treatment, when the water withdraw from wet to be dry, we keep the previous time, the temperature, use the previous time is wet temperature put in there. Okay, that's
Ah,
the reason when you get the next phase to get in, your temperature a little bit different, but not a big difference. Okay, that's the reason. Another thing is now you test in case only for tidal flow. When you get a heat, right?
yeah.
So you get a surface forcing heating. So heating the heat the wet point, they don't heat the dry point. Because dry, you don't do any calculation, right? So that's
Yeah,
why
right.
when you get a water flooding in there, you get a temperature from the wet to become the dry, right? For dry become the wet, you get the water. But when you from the wet become the dry, you just keep a previous temperature. Okay, that's the reason you can see a little bit difference over there. Okay, you understand what I mean? But then
Yeah.
Dr. Lee was also to show you, said because the reason we use minimum depth. Okay, all the wet dry pond model need to use the minimum depth, right? But minimum depth is one you couldn't look at anything in the minimum depth. That's just make the model system continue wrong because you get a slope, right?
Yeah.
If you completely become the dry, the sigma coordinate not valid anymore. Because you vertical, for example, your vertical had a 10 layer, right? You divide a 10 layer. You suddenly become a dry. That's a layer is zero. You understand, right?
Yeah.
Now there's a problem now. So then your sigma coordinate you could, transformation all broken down. So you couldn't get a depth 0, right? Because you divide by depth. If depth 0, you divide by 0, then value will be infinity. So that's the reason you put a thin layer, but you put a thin layer, you don't want a layer too thick. If it's too thick, you can change your dynamic because this layer is not a true layer. It's a layer just for model continue wrong. Right? So that's why they put a thin layer, like we put a 5 centimeter layer, right? But sometimes, before when the wet dry point develop, you can go back look like article describe the method. So the first person they put a 20 centimeter. They put a thickness of a 20 centimeter. That's why the model always stable. You don't have a problem. But however, 20 centimeter can start mixing. Right? Because you without 20 centimeter, you can get a mixing. So that's why you can change the dynamics. So that's why for this layer, you want to make the layer as thin as possible. Okay, we do a lot of testing. We find a 5 centimeter. You can keep the most dynamics, not change a lot. Okay, that's why when you look about a plot, you should not include like he said, don't include the minimum depth in reaching the temperature in because that's was a model wrong for just for stability. Okay, you have to remove that. Understand?
Yeah, I understand. Thank you. Right.
That's why I will tell you you will question too, how does it determine the temperature and the dry node? That's the way to draw it, Flooding, right? From this point becomes dry, from dry becomes wet, right? This temperature is advective. Then it becomes wet, they can have the heat flux in. Okay, it's not only advective. If they still keep it wet, they can heat the budget in the surface. Okay, when it becomes from wet becomes dry, they just advective. But advective water, you keep the previous temperature there. They make the land have the temperature. Okay. You
Yeah,
understand? Okay.
yeah, I got it. Yeah, very, very thank you.
And also in this semester, Dr. Chen also provide a lecture regarding the wet dry method. So you may see that lecture in week 6. So in that lecture, Dr. Chen detailedly introduced how FVCOM treat the wet dry point. So you may see more details in that lecture, so lecture 6.
Okay. You're good. You learn FVCOM, you're already able to run FVCOM. That's good.
Mhm.
Thank
That's
you.
That's a good question.
good.
Okay, I stopped sharing my screen.
Mhm.
Yeah.
So any other question?
I will sharing my
Mhm.
presentation. I have a question about the turbulence model.
Okay, good.
In class, I learned about two turbulence closure model, Malloy Amador 2.5 model model, and K epsilon turbulence closure models. What are the key differences between the two models, and how do these differences affect their applications? I can't understand in lecture, so I want to know about that.
Oh, okay. Dr. Lee, you want to answer the question? Or you want me to answer the question?
Dr. Chen, could you answer this one? I think you are good
Okay,
at
I think you are still doing excellent work. Post question. I hope you can post a question on the discussion board so other students can see your question. Okay, I think you did excellent work to make that's also make the course more informationable. Okay, So I can address the question for you. So they had two type of turbulence closure model you mentioned, you see here. One is called Meller-Yamada. That's developed by Meller, George Meller, and Princeton. Another one, K-epsilon turbulence model. Both model concept is most similar. Okay. The key
Okay.
issue is no first model. There was a there are a lot of discussion on the two model. Okay. I can tell you the history when they developed. George Meller model, you look at the two equation. First equation is called, I think something you write it down probably not correctly. Oh, no, yeah, that's correct. First equation is a turbulence kinetic energy equation, Q square, right?
Yeah.
Second equation is energy, turbulence energy times the mixing length equation. But you look at the two equations together, if you learn the mathematics, if you have a two equation, you want to solve equation, that two equation must be independently, right? But that two equation is not independently, right? Because if the equation for air, for example, the mixing length, that should be independent as the turbulence energy, right? Q square. But then you look at second equation, that's Q square times the air, right? That's why it's not fully independent because there are two variables timed together. That means the two variables that's related, right? That's coherent. That's why turbulence equation, you look at the equation here. So then that's two equations not independent, mathematically not independent. But physically, two equations represent the same thing. You look about turbulence closure model has three things you have to be in mind. One is production of turbulence. So-called turbulence production, right? So you look about the Meller-Yamada model, you see the right side term, you see there are two production terms. One is shear production, another is buoyancy production. PS, PB, right? So then there will be minus epsilon. Epsilon is a turbulence dissipation, right? Dissipation. That's why they have this turbulence source for turbulence. That's a sink for turbulence, right? So you look at this equation here. You look at this equation and the K epsilon equation. You see that's most identical. You can see there, right? You can see there, but Meller-Yamada level 0.2 level, they will think about, mixing, after mixing not only be affected vertically. You see, this term only consider vertical diffusion term, right? But this one includes horizontal advection. They think a turbulence kinetic energy can be advected by the currents from one side to another side. Okay, but then the problem is you run the most model, that turns not very important. That's why you can see most people, a lot of people use like a Meller-Yamada, even the turbulence model, they don't turn on the advection turn, that turn here. Okay, but Meller-Yamada is different from the K-epsilon. You see here, they also have a advection, but this one don't have horizontal advection. Right? The only thing, there's a whole K-epsilon model shown, all the mixings vertically. Okay? It's 1D, one-dimensional. They not, this vertical mixing not be affected by surrounding water. Right? Only vertically. Right? Now vertically you get a shear, velocity shear. Right? So also you get a buoyancy, a production. Because buoyancy production means, okay, if water is unstable, heavy water about the lighter water, they get overturning, right? That can cause turbulence, right? the physics, you know, to create the turbulence production, dissipation, send two equation. But K epsilon model sink, okay, it's a whole mixing is a one-dimensional problem. Okay, no, many another model sink, that's the advection can affect it. This mixing happen, surrounding water can affect turbulence kinetic energy. Like energy can be moving from one side to another side. So many of that model saying that turbulence is three-dimensional problem. K epsilon saying that's the one-dimensional problem. Okay. Then
Okay, thank
another issue, another thing. So K epsilon model, you know, they don't use the mixing length because the mixing length is very hard to define, right? So it's very hard to define kind of mesoscale mixing length. How you define? Nobody know, right? You see
Yeah.
what I mean? That's why in the physically, if you look about the physics, Miller-Yamada model, this one here, you know, first thing, the weakness, these two equations related. The second problem is the mixing length, very hard to define, right? So you look at K epsilon model, you see, turbulence can, they, you know, European people, K epsilon model is popularly used by European people. The reason I keep this name for K, they talk about K is just like a Q, okay, right? So the problem is that European people, you know, use the K called kinetic energy, kinetic energy, right? That's why they instead of use the Q, they use the K, but same thing. Just the way they use different. Okay. So then instead of solving the mixing length equation, they solve the turbulence dissipation equation. Right? Dissipation and the kinetic energy, that's independent. Right? That's two different scale things. Turbulence is caused by the shear. Buoyancy, they come on the shear called turbulence, but a big eddy, right? Big eddy separation, small eddy, the small eddy then go to the epsilon, the turbulence, the diffusion, right? That's why they use like a epsilon equation there. Physically, it makes sense, makes sense, but very similar. You look here, you take this turn out, take this turn out, take this turn out, vertical advection, horizontal advection turn out. You see, that's the equation, very similar for this equation, right? That's why, you know, if this one just you kind of make a long story short, just two turbulence equation very similar. Okay, so you know then one, you know, K epsilon think of one dimension mixing. Mixing was fully one dimension, not related to surrounding water. But the Miller-Yamada think about it is related to the surrounding water, they had advection, right? But in fact, results come out very similar. You know, so I was encourage people use K epsilon because this model, you know, more physically makes sense. But a lot of people use the Miller-Yamada, right? But the US people, because they find it's not much different. Okay. Another thing is, you know, you look about FVCOM, FVCOM has a lot of version for K epsilon for the Miller-Yamada. We include like a general turbulence model, right? Is in the coding. This all the model, most different based on the criterion for the mixing, right? No, original Miller-Yamada model, K epsilon model they developed. You know, this simplification model I write here, but in the FVCOM coding, you can call like a general turbulence coding. They have a much more complicated model than this two. Okay, but that model, how different for this two model? This only different by criterion for mixing. You know, this model criterion mixing is Richardson number 0.25 quarter. Because you know, physical, if you look at Richardson number, you know that the mixing, when the Richardson number is smaller than 0.25, water starts mixing, right? So that is a laboratory experiment. But in the real world, people found that no, even Richardson number equal to 1, they can start mixing. Okay, that's why you get a different kind of temperature model come out, like a Richardson number, they get a criteria Richardson number 0.87, number 1, right? That's why you can't have a different kind of metal amount, a different kind of K epsilon. Okay, I tested all the model. Okay, no matter what you choose, performance difference is very small. Okay, right? Even they make more sense for you, get more mixing, but still similar. That's why, Melia model and Kexel model is good for tide mixing. Because tide mixing is completely caused by the shear velocity shear, right, in the bottom. That's why this model can really really accurately resolve the tide mixing at the bottom of the layer. But for wind mixing, sometimes working, sometimes not working. Okay, it's not a perfect model. Okay, that's why So if you people interested, you can be develop a new model for wind mixing. I think about that. Okay, I was always think about we should develop a new mixing model for surface mixing. Okay, because this model, most of the problem is this two model not able to resolve a sharp thermocline. Okay, you got a water surface mixing, you got a sharp thermocline, they not resolve. They got a most diffuse thermocline. Okay, so something that happen for their instability function for the penetration they choose. Okay, but you should, bottom line is that you should understand better than nothing, but not a perfect. Okay, don't trust too much about this term closure model.
Okay.
So I answer your question.
Yeah, thank you.
I can tell you the story. This model, when a Melia model was developed, okay, a lot of scientists think of this model is trash. Okay, no one use. For most, he was developed like I think it's 1987, 86, something like this, but nobody used that because most people think that two equations not independently. Okay, that's why nobody uses this model. So then when I do my PhD thesis, I want to try to do the tidal mixing. So then I test the model, use a tidal mixing, use an idealized case. You use theoretically how the tidal mixing, bounded body level, how thickly they are, how mixing they should be. So I use the model very successfully to develop the tidal mixing. So then after my success, okay, I show the people that the model can use coastal ocean. Before or study, most people use constant eddy viscosity. Or some people use the Richardson mixing, okay? Richardson mixing, but no one uses temperature closure model. So I was a person, to verify this model is really working for tidal mixing. So after this one, so after I did that's why in the US, most of everyone model started using the temperature closure model. So you can go look at the paper, go there, is 1992. But my results, I published my thesis in 1992. But a lot of people come from 1993, 1994. Okay, they use temperature closure. But they all kind of ideas come from my thesis work because I published it late. These people publish it first. Right? When you was a graduate student, right? You're working on something, you find something interesting, you defend thesis. So people quickly use your method to do the work publish, all right? But you are published slow, right? Then later people say, oh, you reference other people's work. No, it's different. Okay, that's why we had to find some way to how to protect it, student thesis, right? Work, dissertation work. Okay, like my PhD student, he do like a tidal pumping work. Okay, like water tidal mixing cause the nutrient flux. He first person said tidal pumping. So then some people look at his thesis because he had not passed his PhD defense yet. Some people already published a paper tidal pumping. You see, right? That's could be happen. Okay, if any other question?
No. Oh, thank you for your.
Do I answer your question?
Yeah, thanks for answering.
I have a question.
Mhm.
Can I share my screen?
Yes,
Okay.
please.
Okay. I have a question about time integration method. In lecture 3, we learned that in explicit time integration method, a difference occur in the vertically integrated transports between internal and external modules when different time steps are used for the internal time step and internal mode and external mode. To eliminate this difference, we learned that calibration is applied equally across all layers. I think that this calibration might lead to errors in each layer, like this figure. Is my understanding correct? And if accuracy is prioritized, would it be best to set I subsplit to 1? Yes.
That is a good question. Okay, first things, the reason we have mostly because we want to increase computation efficiency. Now, definitely, if you set like a three, coefficients of 1, you use the external mode to do the calculation, you definitely can get you don't have an error, you don't have a numerical, difference, because two mode, just you don't have a problem. You can that's get the best solution definitely, right? You don't have a two mode adjusted the problem anymore. You don't need to adjust it anymore because you can send time step, right? The reason we do the mostly because we want to see because if you solve this time, because surface graduate, the publishing speed is really fast. In the shallow water, they publish the square root of GH. G is gravity velocity, gravity, acceleration coefficient. Then H is the water depth. So you look about 10 meter, right? You look about G is like a 9.8, like 10. You look at 10 meter depth, then your speed, propagation speed, gravity wave about 10 meter per second. 10 meter per second with the propagation really fast. 1 second, you can propagate 10 meter. So your model need to capture this fast propagation wave. You have a very small time step, right? Because 1 second can propagate 10 meter. So you want to catch the propagation wave, you have to be, very small time step. Before the like Princeton model or other model developed, long time ago, people try to avoid that. What do? They don't like sea level included in the model. They put the least lead in the surface because your surface gravity wave had a converging diverging cause the surface gravity wave, right? They don't like the water surface converging diverging. Then they no wave. Then they can use a longer time step. Like like before the run, they had a model called span. They use this method. Ron's model, the regional ocean model, Ron, their first version is the least lead. Okay. So then, however, surface ground wave is really important for tide simulation, right? You have to include that. But the propagation is so fast. That's why you have a very small time step. But if we all use the small time step, if we have a larger domain to run the model, it's computation efficiency very slow. Very slow, right? You're not able to do that, right? So that's why, so we said, okay, because only important, most ocean have two modes. One is the surface gravity wave mode, another is the internal mode. But internal mode, their propagation speed is very slow. But the surface gravity wave mode is propagation very fast, right? That's why you want to distinguish two things. So then we try to solve it, because this surface gravity wave, the propagation proportion transport, because the surface, sea surface, the proportion transport. That's why if we can develop a vertical averaging equation, a vertical transport equation, we can solve the equation, we can determine the sea surface, right? But that's why you need a small time step. But two-dimensional thing, vertical transport is two-dimensional. You only can solve one layer. You don't need to solve many layers, right? Because hello water, you got depths like a 20, 40 layer, like a 300-meter depth or something. So you transport. That's the reason we can have a two vertical averaging mode only solve for sea level, right? For the surface gravity wave. That means a small time step. Then because we found internal mode, the propagation slowly. So we can use a longer time step, solve the internal mode. That's the reason we get a mode slip method. Okay. You understand right now?
Oh, yes, I understand.
So now the question come out is now how you make adjustment. Right? That's the question. Now, if you want to have a barotropic mode, barochromatic mode, now you want to be internal mode. So because it's two time step different. So which one's more accurate? Definitely the one with a short time step, the one's accurate. Right? Because the time step is short, right? They're accurate. Because your time step is longer, you're not very accurate. But if we run a two mode separately, we don't do adjustment. So then there's a 3D circulation, a 2D circulation can go to two direction. Different, right? So that's the reason some kind of model right now they probably use, they get a two-dimensional result, 3D motion is different. Right? So that's the reason when a Princeton ocean model developed, they said we need to adjustment. We want to make sure your 2D mode, 3D mode is same thing. Your 3D mode, vertical average, you go back to 2D mode. That's the reason we need to adjustment. So then we adjustment is said, you have to have a vertical average, the transport for 3D mode need to be equal to your transport calculated by the 2D mode. Right? But then you cannot choose a very long time. For example, you run a 3D, 2D mode as 3 seconds, but you run the internal mode for 1 hour, right? You couldn't do adjustment because they already go to two similar solutions. You're not able to merge it anymore, right? That's why you cannot be too long. That's why we choose. Then we have to choose some kind of ratio. How many time step you need to run? Okay, you can keep the computer efficiency. Meanwhile, you want to also make sure solution converging. Okay, so the reason we use the two sleep mode is the reason because we've got a computer efficiency. So you said no, if you said a 1, yeah, it's good. You don't need to worry anymore. But then you lose the computer efficiency. Based on our testing, most case you can choose a ratio about 10, right? 10, you can use 10. That should be okay. So that's the reason, most serial code is good for shallow water. Okay, when you go to deep ocean, like Arctic Ocean, global ocean, you don't want to use the most serial code to solve the problem. The reason because you have to adjustment in the vertical column, but you have to adjust every layer, right? For example, your deep ocean, no motion, velocity equal to 0, but after adjustment, it starts motion. but also adjustment locally. Each volume is different adjustment. So because your depth different, your adjustment different, you can cause converging, diverging in the deep ocean. Then it causes some surface wave, propagation of surface. That's a numerical error, not a true wave. So that's why when we apply to deep ocean, we don't use small slit curve. We use like a semi-implicit solver. Okay, then you don't need to adjust anymore. Okay. Do I answer your question?
Oh, thank you. I have no question anymore.
Okay.
Thank you.
Yeah.
Thank you so
Good.
much. This is a very good question.
I think you three people prepare very well. I
Yeah.
suggest you people put your question on the class, the discussion board, because we only had your three students was here. So then we hopefully other students can see that. Okay. But next time we probably record. Right?
At the beginning of the meeting, I also do the record, so that other students who didn't join this discussion will see the video.
Yeah, I can see the video. Okay, good. Okay.
Mhm.
Okay, yeah. Okay, good. So we got a 1 hour almost close to. Okay, a good time, I'm really happy to see you three students. Okay, that's a new student, right? How many years you stayed in High University right now? Fourth year? That's your fourth year for see the Professor Wu's lab?
Yeah, it's the first year now.
Okay, good. Okay. I think last year, student like a couple students take a course, they do excellent work. So after taking the course, then also, King come to become my student right now in the US.
Yeah, he did a great work.
Oh, he did a good job. Now he developed like a 3D assimilation method, data assimilation method right now. So yeah, it's a good thing. Okay. So when we get a time here, Dr. Lee, Professor Lee, and I can go to visit your Korea, give you a lecture over there. Okay. Yeah. Okay, good. If you don't
Okay.
do we have another further question? You have any other question? If you don't, we can wrap up.
Yeah, so if there is no more questions, so we may end it up here. Feel free to leave a message or questions in the discussion board, and we will have the same discussion next week. So see you then.
So I think post your three questions, put on the discussion board. Let other people see that. I think your three students did excellent work.
Yeah, that's very good question.
Yeah. Okay.
Oh, okay. Thank you for your time.
Okay, thank you so much. See you next week. Bye-bye.
Okay, thank you for your lecture.
Thank you so much.